Howdy everyone, and welcome back. And we've been talking about magnetic fields for a little bit, and today we're going to keep moving on with that. We're going to talk about an application, things you can do with magnetic fields beyond what we said last time, specifically about magnetic induction, and that's governed by something called Faraday's Law. So we're going to talk about that. We're going to talk about some applications. Actually, some of the applications are really interesting. Things we likely use in our everyday life are really fundamental. Actually, would have been a lot harder to actually teach this particular subject, say in the 1800s, 1900s, when people knew about this, but they had some limited applications. There's some really important things like electrical generators, but for us currently, it's actually how our wireless chargers work, is actually using this sort of same principle. So let's talk about it. Let's talk about some applications with it, and then we'll do some problems. So let's talk about Faraday's Law. So here, this is Faraday's Law, and what does it say? Well, we have a loop of wire here, and it's uncovering some type of cross-sectional area. I have some loop of wire. You can cut it across. There's some type of cross-sectional area. It has a magnetic field going through it. Now, if this magnetic field is constant, this loop's constant in its area, nothing really happens. But something really interesting happens when you start changing what we call the magnetic flux. Now, we talked about electric flux before, but it's really the amount of electric field going through a certain area. So it's in this case, the magnetic field times the cross-sectional area times some type of angle. Again, it's the area that we care about is the effective area. We take some cross-sectional area. It's kind of like we take a light and it shines a shadow on the wall. We turn it, then that's actually less of it. It's actually getting hit by that light, or in this case, magnetic field. So less of it counts. So this is what we mean by a magnetic flux. And so something is really interesting happens when this magnetic flux changes. So that can happen in a ton of different ways. You can increase, decrease the magnetic field. You can take this loop, you can make it bigger, make it smaller, maybe you just turn it. But if you change the magnetic flux, so that's this term here, and number of loops, whatever. But if you change the magnetic flux, you'll actually induce a current, or this specifically is an EMF or voltage. So you'll create a voltage in this loop. So this is a wire, and, it's a complete circuit. Some voltage will be created and a current will be created in this loop just from the magnetic fields passing through it. And so it turns out that it's end up being really, interesting and more practical. I have a little prop here. I have this is my phone charger. Well, it's a lamp. It has a phone charger connected to it. And you can see it's a little circle. There's a coil of wire in here, and in my phone, well, I put it somewhere, but there's a coil wire in it too. And so this is going to be creating a magnetic field and then changing that magnetic field, maybe increasing it, decreasing, maybe changing the directions, and that's going to create not a magnetic field, it's going to create a current. Well, actually that will create a magnetic field, but the point is that this is going to be creating a magnetic field that's going to be passing through the loop in the phone, and that's going to create a current that's going to create a voltage in the phone. That's actually how it's able to transfer power over. So there's a few other applications. We'll get to there in a moment. When I put my pencil. Okay, here we go. But the change in magnetic flux creates a voltage. Now, there's a lot of work to figure out what direction that current is. That's actually really what this negative sign represents. Is actually me creating a voltage that opposes that change in magnetic flux. We'll talk about that extensively, what that means, because it's something that's pretty hard to talk about, and maybe not talk about. It is probably, but it's really hard to get your mind around it in the beginning. We'll get to that in a moment. So we're going to work a little bit with some other applications of this called inductors. There's a new type of electrical component we'll use called an inductor. It has some inductance L. We have resistors, we have batteries, we have capacitors, and now we have inductors, which are really just these little loops of wire. And you can imagine that the loops are going to create magnetic fields, they're going to interfere with the other loops, and that's going to actually be useful in terms of an electrical component. But here's just a few terms that we'll use in a bit. Okay. So let's start talking about how you actually determine the direction of the current. Now, it's not simple. There's a lot of different ways you can change the magnetic flux, but the key principle is that current goes in the direction that creates a magnetic field that opposes the change in flux. So when you change the magnetic flux through a loop or whatever, it doesn't like that change. It actually wants to oppose that change. So if I have a magnetic field going through this way, we're going to do this in a particular example in a bit, but say I was decreasing the magnetic field, it actually will want to keep it the same. If I'm decreasing the magnetic field, it wants to increase it. It wants to keep it the same because now you're making it smaller. You've changed it. So it's going to be like, okay, I want to, since this is getting linked in this way, I'm going to actually start making a magnetic field that points in the same direction. I'm going to try to keep it the same. And from there, we can get the direction of the current. We're going to have to use a few right-hand rules along the way, and keep a few things straight in our head. But let's do a few examples to see what I mean. So let's do this actual first one, what I've written down. So you have a loop that's pointing straight up, and then you turn it. So now it's going to be as being some diagonal, but you can see the magnetic flux, the effective cross area is now decreased. I have something staying straight up to the light. It's going to create, the shadow essentially the same size as my hand as long as the light's in parallel. But if I go and turn my hand, you can see even just in the camera that effective area, the cover amount it's actually covering on your screen that you see is decreasing. So that's what's going on with this loop. So the magnetic flux is changing. So how we do these problems is the first thing we ask, is the magnetic flux increasing or decreasing? Then we're going to figure out, okay, what direction is this thing that we want to make a magnetic field, which is going to correspond to that first question. And once we know the direction that it wants to make a magnetic field, that will inform us using the right-hand rule what direction the current is. Okay, so let's do that. Let's do all three of those steps really quick. Okay, I'm taking something, I'm decreasing its cross-sectional area, I'm decreasing the magnetic flux. I'm decreasing that area, so the magnetic flux goes down. It doesn't like the magnetic flux going down. It actually wants to keep it the same, so it's going to make a magnetic field pointing in the same direction as it's already going. Okay, so I think hopefully that makes sense why the magnetic field has to be in the same direction. That would keep the magnetic flux constant. Of course, it's not actually keeping it constant. It's just trying in vain to make that so, but it's not going to really happen. But again, what we're doing is really just trying to trace back and figure out what secondary magnetic field that this loop creates. So it's going to be in the same direction as this magnetic field is already pointing. Okay, so I have a loop like this. Again, it's really hard because it's something that's really in reality 3D. It has magnetic flux passing through it. It wants to create, magnetic field passing through it. It wants to create a magnetic field in this way. So what direction does the current have to be going to create a magnetic field going this way? Well, then we can use the right-hand rule, and this is the one with you point your thumb in the direction of the magnetic field and other way around. You point your thumb in the direction of the current, wrap your hands around, that gives you the direction of the magnetic field. So I have a loop like this, so we can test, essentially we can go clockwise or counterclockwise. So just pick a point, I have my loop, and magnetic flux is going in this direction or whatever. Say I was trying to guess counterclockwise. Okay, I wrap my hands around, and really we're talking about the direction that it's going to create a magnetic field in the center of the loop. So I wrap my hands around, and if it's going counterclockwise, the magnetic field will be pointing out. So writing that another way, so this is actually going to be right. We're writing it. It's weird because I think the picture is very misleading. There's a 3D effect going on that I don't think is so super obvious, but maybe put it up to the camera, make it more obvious. So again, I have a loop here. I want say the magnetic field was pointing towards you guys, pointing towards you, and then I'm turning it, decreasing the magnetic flux. Okay, it wants to create a magnetic field also in this direction to keep it the same. So to do that, it needs to make a current in the counterclockwise direction. We can check that by using the right-hand rule. Pick this point on the top, point our thumb in that direction, wrap it around, and we'll see when we wrap it around, it's going to create a magnetic field coming out into the center of it. So it's going to be very confusing to do this, but we're going to keep doing it. We're going to do it at least 2 more times. We're going to do some problems with it. So it may not make sense at first, but we'll keep doing it enough times until the point where hopefully it does make sense. Okay, so we get this counterclockwise, again, not obvious from the picture, but counterclockwise in this case. Okay, let's do the second example. So we have a loop that's small, and then I make it big. So you have a magnetic field that's pointing into the page. That's what these crosses mean. They're going into the page. So is the magnetic flux increasing or decreasing? That's the first question. Well, the area is increasing, So the magnetic flux is actually increasing. So again, remember the loop wants to decrease it. Well, not always decrease. So remember the loop wants to keep it the same. So to keep it the same, this time it has to actually decrease it because it was increasing. So what direction is it going to make a magnetic field? Well, now the opposite as it's going. So since the magnetic field is going to the page, it wants to make a magnetic field going out of the page. So if it's going towards you originally, it's now going this direction. Again, the magnetic field, this external magnetic field isn't really being overpowered. It's just this loop is trying in vain to keep things the same, like a little person in their little part of the world, and they're trying to keep it the same, but they can't actually change all that much in terms of the overall world. That's maybe a bad example, but that's sort of what's going on. So the loop is creating a magnetic field going out of the page. What direction does that have to be? Well, we can try again, counterclockwise. We pick a point, so like my loop, I probably should have a better thing for this one. My hand is not big enough, but I pick a point at the top, current's going this direction, I'm covering up my loop, wrap my hand around, okay. So again, recall for these loops that the magnetic field is really a three-dimensional thing. There's a point a certain direction on the inside and then pointing the opposite direction on the inside. Again, we're pointing the opposite direction on the outside. So again, we're interested in what's going on the inside, what's going on the inside. That's the direction that we're trying to figure out. Okay, let's go over that again. We have a loop that was small, became big, its magnetic flux increased. So now this loop wants to create a magnetic field that opposes that, so it wants to decrease it. So it's going to make a magnetic field going in the opposite direction as what's going as this external one. So to make a magnetic field going in the opposite direction, it has to make a current going counterclockwise. And we figured that out, wrap around our hand. If we have something that's pointing forward towards you to make a magnetic field coming out here, it has to be counterclockwise. If we wanted to go this direction, it would be clockwise. So, okay. Clear as mud. So let's keep going. Let's do another example. We'll have to keep doing these examples because it's very, very unclear the first time you learn it, the first few times you learn it. Oh, I mean, I think it makes sense to me after, now after thinking about it for something, like 8-9+ years. So we have a loop. Now, this loop is staying the same, other than the fact that this external magnetic field is now decreasing. Okay, so is the magnetic flux increasing or decreasing? Well, it's decreasing because the magnetic field decreased. So it wants to keep it the same, recall. So it's going to want to point a magnetic field in the same direction as this current external one is. So to do that, I have my loop here. If I want to make a magnetic field going into the page or going in away from the camera lens and pointing towards this wall, I actually have to go going clockwise. Again, we can check that. Pick any point on one. Pick any point on your loop. I want to pick the top one again. If I instead go to the right, which would indicate clockwise, wrap my hand around. When I wrap it around, I know that the magnetic field is going to be going in while pointing to the center, and again opposite on the outsides. But again, check it with the right hand rule. Okay, we're going to keep going with that, but hopefully that gave us some type of knowledge so we can start. You're just going to have to practice it a lot. You're just going to have to try it a lot for yourself. Then hopefully it becomes a lot more obvious. Okay, let's keep moving. Let's do a problem. So we're going to do one of those where we use that practically in a bit. We're going to do a couple problems with circuits, and then we'll get back to the stuff we just learned. So this is an RL circuit, and RL meaning it has a resistor and an inductor. An inductor is indicated by L, which is, well, it actually stands for inductance. So what is going on? What is an inductor? Okay, I have a loop, and you notice I have a bunch of little coils. So we talked about coils being affected by magnetic fields. We also talked about coils creating magnetic fields. As you can imagine what happens, you have some type of current that goes through. It's going through these coils, and okay, that's going to create a magnetic field because there's moving charge. I don't know if I'm getting the direction right. It's not super important at the moment, but that magnetic field is going to affect the other loops. It's going to affect loops way over here when it starts passing through them. And that magnetic field may not be the same. It may change over time due to things happening externally, or also if you just have an inductor, it'll change over time because it'll interact with itself and change it over itself and change the current just by itself. And so you have a changing magnetic field, so it's going to create other little currents. Use black again. It's going to make other little currents. They're going to usually, oppose this current at first. And the other parts of the loop, so this is an electrical component that interferes with itself and actually doesn't like. The best way to describe it is it doesn't like changes in the current. It actually would be perfectly fine if the current was staying the same all the time. And essentially, an inductor is kind of like the opposite of a capacitor. Capacitors like when the current is changing a lot because it can't move charges really far over, so it needs to move them around to do anything. And eventually, if it gets full of them, it can't do anything. Inductors are the opposite. If everything's constant, everything's the same forever, it doesn't need to change anything. It just sits and does nothing. But things are changing like a lot. No, it doesn't like that at all. Stop with the change. So again, kind of the opposite of a capacitor. Capacitors like change, inductors don't. So we want to figure out some things with this RL circuit. And again, we can put in whatever R's and L's we want in the end. That's not going to matter too much. Well, we have a circuit that's in series. At some point, this is open, and then eventually it closes, and that's going to finish this circuit so things can actually happen and go on with it. So we want to figure out the voltage over the resistor at t equals 0 and at this other time, and it's going to be, we'll work it out. I think we need to get this one first, and I think everything else will be a bit more obvious. So we can actually write down an expression for the current. Now this is something that you could derive using Kirchhoff's laws and writing down the voltages of all these things. For the non-calculus based approach, that's not super doable, but let's at least draw out what this current looks like so we can get a sense of it. So we have this maximum epsilon over R current, and this looks like 1 minus e to a decaying exponential. So at at t equals 0, that's actually going to be 1 minus 1, so it's going to equal 0, and it's something that decays up and asymptotes to some maximum value. So you have essentially no current going through. The inductor really doesn't like going from no current to to some current. Things are happening and wants to really cancel all those changes. But eventually it settles down and things stop changing so much over the time, and essentially doesn't do anything. And the current just acts like there's just an inductor. Oh, sorry. The current acts like there's just another resistor, which is this is V equals IR here. Okay. So that's sort of an explanation of what's going on. So we don't have to necessarily derive that, but we can sort of work with it a bit. So we want to find the voltages at a few different times. So V equals IR is always true. So I get this current, we get it times the resistance. Okay, we can write down, get rid of that little resistance. So it's just this voltage times this 1 minus epsilon stuff. And then we can put any time we want in. We can put any time, so we can put t equals 0, the one that we are asking over here. We can put in this tau. Okay, if we put in t equals 0, well, we get what I was saying before. There's no voltage. And why is there no voltage over the resistor at t equals 0? Well, the voltage drop, instead of happening in the resistor, all of it is happening at the inductor. It really doesn't like the change. So it's really doing a lot of work to oppose all of this change. You're creating magnetic fields that oppose the currents. Okay, all the voltage drop happens here. But over a long period of time, eventually we get back to normal V equals IR. Eventually, this is causing all the voltage drop. And then there's this weird space in the middle where, they're both kind of doing something. Okay, but then we can put in tau. So again, this is just a time constant for capacitors. It was R times the capacitance. Well, it turns out for inductors, it's L over R. Okay, something you could derive, but maybe we don't care so much at this point. Okay, only difference is we get 1 minus e to the negative 1. So the tau's cancel here. We just get the negative 1. And then at this tau time here, where this is tau, we get that the voltage over this voltage over the resistor is 3.79 volts. Okay, and it's something using Kirchhoff's laws, we find that the voltage drop over the inductor counts for the rest of it. If you're interested. Oh well, we're gonna do that. So the voltage over the inductor. Well, we're gonna do Kirchhoff's laws. I forgot we do this part of the problem. But you can get this by knowing that if you go over all these components, so if I add up the voltage from the battery If I add the voltage from the inductor and then the resistor, then I know that they all have to add to 0. The energy doesn't disappear anywhere. It actually just, the energy from the battery goes to the other two components. Okay. And we rewrite this so that we get the the voltage of the inductor. We've already written out an expression for the general voltage for a resistor. That's this stuff. So what happens is that we just get rid of this first term. We're just left with the exponential term. So what does this look like? Well, so look at like the opposite. Again, this is time here. I didn't label that. It's going to just be an exponential decay. It's some maximum value. This is just going to be epsilon. So this is not VR, this is VL. Could be some epsilon, and then it's just going to asymptote to 0. Okay, so again, inductor is doing a lot at first when there's a lot of change, but when there's no change, things settle down. It's not really doing anything. Okay, we can put in the same times. Put that in for VL, it's 6 volts, so it's dropping all the voltage of the battery. And then at t equals this time constant, it's 2.21. So again, these two together still sum up to 6. We've actually enforced that here. That's what this expression does. But, again, inductors are doing a lot at first. Then, over time when things start changing so much, then they don't do so much. That's sort of the key point here. Okay. Okay, there's any more? No, there's no more. Okay, let's do one more thing. So inductors, like capacitors, can store potential energy. Again, it's putting things into a slightly uncomfortable position, like capacitors are holding charges together. Well, this is making currents as opposed to each other. It's storing energy in magnetic fields, so it can really store potential energy just like capacitors can with those magnetic fields. Okay. So we can write down the potential energy that an inductor stores, 1/2 Li squared. It feels like, we get a lot of these kind of equations. For capacitors, it was QV squared, so voltage mattered, and then charge was one of the basic things. Well, now it's current and inductance. So there's, some of symmetry there. So this problem, we're just doing something really basic. We're just told if we have a current, we have the potential energy, what's the inductance? So we have our equation. For the potential energy of inductor, we can go solve for this inductance backwards. We don't move that. We move everything else to the other side. We get 2 times the potential energy over I squared, and then we get some number in henries for inductance. So the SI unit for inductance is henries. And it's just one of those things that, people picked it. I'm sure someone knows the name at some point. But okay. So the next question, what if it was 3 amps? Okay, you put it in the same equation, okay. But at this point, this problem is just to highlight that inductors store potential energy. Maybe that comes up, maybe it's important at some point. Certainly in real life components that you can use capacitors and inductors for kind of dualistic purposes, but they both store energy in their own different kind of way. One in electrical energy, one in kind of magnetic energy. We had talked about magnetic fields themselves can't do work on charges, but they can sort of put things in an uncomfortable position that then can move back. So you can have potential energy with magnetic fields, although it's a little weird compared to electric ones. Okay, let's do one more problem. This is going to be something we're going to use. It's going to use the skills from the first problem that we did. Now, there's a lot of things to keep track of, so let's go over it. We have a square bit of wire, and it's going to fall into magnetic field. So there's no magnetic field passing through it now, but eventually there will be. And so when it's down here, it'll be partially covered. And you'll notice that it goes from no magnetic field to some, and then complete, having a lot of magnetic field. So you notice, okay, it's going from zero magnetic field to a lot of magnetic field, so the magnetic flux is changing. So this thing is going to make a current, and it's going to make a current that goes around. It's going to make a magnetic field. So the other thing that's interesting is that there's another, if you keep going with that, there's a feedback mechanism. Okay, this thing is going to make a current. I'm just picking a direction, but I don't know whether that's the right direction. We'll maybe get that in a moment. But remember what happens when we have moving charges in a magnetic field. So we have a current now being generated. That current is going to get affected again by the magnetic field. So the magnetic field is going to actually exert a force on this loop just from the fact that it has a changing magnetic field, well, changing magnetic flux more technically. That changing magnetic flux is going to make a current, and then the external magnetic field is going to exert a force on that current. So this thing is actually going to get, we're going to figure out it's going to get slowed down in a bit, but you can actually make things that slow down just from magnetic fields. Now again, you have to have a changing one. Either this magnetic field has to be changing or the amount in it has to be changing, something like that. But in this case, the amount in it is going to be changing, which is going to make the magnetic flux change. Okay, so let's go back. We want to find the terminal velocity. So the terminal velocity for anything happens when all the forces equal 0 and you have something in free fall, and now it's not going to go any faster. The acceleration 0 because all the forces cancel out. So when we have to talk about terminal velocity falling from an airplane or falling from space, eventually the air drag equals the force of gravity, and those two things cancel out, and then you have some just, this one velocity that sort of a maximum. Maybe you can figure out a way to go faster, but for free fall ends up being the maximum. Okay. So to have a terminal velocity, you have to have two forces opposing. So we're going to find that let's just assume that the magnetic field is going to be opposing. Again, gravity is always going to be down. This thing has some type of mass, and the magnetic field, the magnetic force is going to be pointing up to oppose it. I think we should do a little bit of work to convince ourselves that is going to be the case. But we have to do a little bit of work to figure out what this sort of stuff is. So the force due to gravity, that's just mg, sure. But recall from the last video, last section, that we can take the magnetic force as from a wire as being the magnetic, the current, I don't even know what I'm looking at. The current times the length of the wire, so what's relevant. So only this bit is going to end up mattering, the width of this wire. It turns out, just like when we do the problems before, that these two little bits, when they're both in the magnetic field, they're going to cancel each other out. So this is going to be the only bit that we really have to care about. The length of the wire just in the width times the strength of the magnetic field times the sine of theta. So the current can only be pointing left or right, and the magnetic field is coming out of the page. So then we could have a 90 degrees. So this is going to be sine of 90 degrees, which is going to be 1. But how do we figure out how much current's going through? So presumably they've given us the width and the magnetic field, but who knows? How do you get the current? Okay, we're going to do a little bit of work. So that's going to be happening over here. So we can write V equals IR, separate out I to the other side by dividing by R. So we want to find this voltage, this electromagnetic force, or it's just voltage. Well, we use Faraday's law. So recall that it was the number of loops times the change in magnetic flux over the change in time. That's exactly what we wrote down originally. Negative signs here, that's just to remind us that it's going to make it opposing the change. So, and we worked out how to get the directions for that. Okay, but what is the magnetic flux? So there's going to be some change in time and some magnetic flux. Okay, well, the magnetic flux is the magnetic field times the area. So what is this cross-sectional area? Well, it's a square, so it's going to be the length times the width. And so I have these kind of delta terms here, and we have to do a little bit of funny business. Now, in reality, this is a derivative, and we really can get, we can, really it's going to be an operator that hits this stuff. But let's think about what's changing. So is it the magnetic field changing? Well, the strength's not changing, so this number is just going to be a constant. It's not changing through time, so it gets to pass through here. It's not changing. So, okay. Is the width changing? No, not really. It's the wire's not deforming anything. The loop's not deforming. But is the length changing? Well, kinda. So what we mean is by the length, let's think about representing how much magnetic field is actually passing through it. So what do I mean? So imagine it's down here. So at this point, this amount now is going to have a magnetic field passing through it. And so this effective length that's in the magnetic field is going to be changing. This is the only, again, the real hard constant L doesn't change, but the amount in that dimension is going to change over time. So maybe L isn't the right one. Maybe we have some variable Y that's representing how much that it says is in there. But it's the point is that there's some variable regarding the magnetic flux here. And when we ask what its change over time is, well, what's the change in a length over time? Well, that's a velocity. So we can just write this as the change in L over change in time is just the velocity in this direction. So that presumably we know that. And that's actually, presumably we don't know it. That's the goal of the question. We need to find the terminal velocity. So that's nice that that shows up in that kind of way. We want to find the terminal velocity. Okay, reminding myself what the problem is. Okay, so we get this IWB. We throw in all the stuff that we found out for I. So it turns out we get a W here, we get a W here, we get W squared. We also get a B here and a B here. So we get B squared, W squared, is terminal velocity over R. So now we just need to solve for terminal velocity. We add this mg to the other side. We divide out the B squared, W squared, multiplied by the R, move that over, and we just get this amount of stuff. We just get a bunch of constants. We get to throw them together. Okay, sure. So let's do a little work. And let's actually show that this is an opposing magnetic. Oh, let's show that's a resistive force in terms of it's actually going to make a force that points up here. I think we just assumed it, but let's actually show that. So we think that's going to be pointing up this way. So let's do that work to show it. So let's think about what happens when we have a little bit of magnetic field in here. So is the magnetic flux increasing or decreasing? Well, it's increasing. It didn't have any magnetic field going through before. Now it does. It's increased. It's gone from 0 to some positive number. So is it going to make a magnetic field going in the same or opposite direction as this external one? Well, it's going to be the opposite. It wanted to keep 0. It didn't want it to change. So this thing is going to be making the magnetic field going the opposite direction. Okay, and then what direction does the current have to loop to make this happen? So again, I just like picking points at the top because they're easy to think about in my mind. So I can either pick left, I can either pick right or I get to pick left for my theoretical loop that's living here. So if I wrap my hand, point it to the right at the top, I get to wrap my hands around, and I'll find that when they wrap around, they will be pointing into the page. So that's what I wanted. So current has to be going to the right on top so that when the magnetic field wraps around, it's going into the page when it's on the bottom. So now let's extrapolate. So again, this current keeps going around like this. So at this point we get to the bottom, it's pointing to the left. Okay, so then we have to use the other right-hand rule to actually figure out the direction of the force. So the other right-hand rule, recall that you point your hand in the direction of the current, you curl it in the direction of the magnetic field, which is pointing out of the page. So point my hand in to the left, I curl it, pointing into the page, pointing in towards me, and the magnetic force points up. So that turns out it really is a resistive in this case. And then you can do the same problem where you switch the direction of the magnetic field. Everything switches. The direction of the magnetic field wants to create the direction of the current, but it turns out the magnetic force will actually still be up. So it doesn't matter whether it's pointing, the original magnetic field was pointing in or out. It's always actually going to be a resistive force in this sort of situation. Okay. I want to spend just a teeny bit of time thinking about another quick application. Now, I certainly charge my phone a lot with, these sort of things. Oh, dropped my pencil. I certainly charge my phone a lot with my wireless charger. I just find it convenient. I don't know, just plop it down. Same thing, AirPods and stuff. But there's another, actually I need my pencil. There's another application that is really, really important, and that's generating electricity. So let's think a little bit about a problem here. So we're not going to actually solve it. I'm just going to do this off the cuff. So imagine I make a magnetic field, and then I have some loop. Oh, I want it to look like this. Looks like this. And it's able to turn around this axis. So I take this loop and I go, whoosh, I can turn it. I have some type of big thing that gets to turn it, and then I can somehow keep the loop, the circuit going regardless. I get to take this loop and I get to turn it. Okay. So what's that going to do? Well, I change the magnetic flux over time, so it's a maximum here. It starts decreasing, 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 0, increasing, increasing, increasing. So I'm changing the magnetic flux. I'm going to create a current. I'm going to create a voltage. So if you can just take something, well, if you have a magnetic field, you can just twist something, you'll create electricity, you'll create a voltage, you'll create a current. And that's exactly how power generators work around the world. I figure out some way to turn something, either that being a wind turbine, that can be a turbine meant for water, for a dam, you have water going through, this turbine comes and spins it. That could be a coal power plant where you get a bunch of steam and hot stuff coming through, it turns a turbine. Or even a nuclear power plant where you get all this hot steam to turn a turbine. This is how we create electricity. And the really interesting thing is that it goes from decreasing magnetic flux to an increasing one. So eventually, in a little bit of time, the current will switch direction. This naturally generates alternating current. It's actually going to be something we're going to talk about in a bit. I'm pretty sure it's the next topic. So this is how we make electricity. It actually makes alternating current, which is a type of circuit. We've been talking about direct current circuits all along, and eventually we're going to switch over. But it turns out this is it's a little important, little important kind of ability beyond the everyday life stuff like charging phones. But I think we should call it there. That's probably enough for today. That's magnetic induction. That's Faraday's law, and what I can talk about. Thank you for joining me. Always appreciate it. I'm going to try to see if I can fix anything in this video, but we're going to go from there. But thank you for joining me. Good luck whenever you're doing. Okay, I'll see you. Bye.